Hello, and thank you for joining us for the Modeling, Money, and Management in the Humboldt River Basin panel. My name is Levi Kreider, and I will be moderating the Q&A session for this panel. During the 2012 to 2015 period, the Humboldt River region experienced one of the worst droughts since 1902. By the end of the irrigation seasons in 2014 and 2015, the Humboldt River at Imlay was dry and water was unavailable to allocate to downstream surface water users in the Lovelock area. At that point, decreed water right holders alleged that junior groundwater appropriators were capturing surface flows of the Humboldt River and that groundwater use was conflicting with the senior surface water rights. In 2015, Pershing County Water Conservation District requested that the court require the state engineer to take action within his statutory authority to address the alleged conflict. These circumstances prompted the state engineer to evaluate the data available and resulted in the state engineer initiating work with the U.S. Geological Survey, Desert Research Institute, and the University of Nevada, Reno to develop improved groundwater budgets at the basin scale, to develop numerical groundwater capture models for the Humboldt River region, and to determine the annual value of water rights not delivered due to capture or other circumstances. Today's panel will showcase some of the work conducted by the USGS and UNR on modeling and water valuation, respectively, and end with a discussion on management implications by Division of Water Resources. Our presenters today will be Kip Allander for the USGS, Dr. Mike Taylor for UNR Department of Economics, and John Benedict for the Division of Water Resources. Please welcome our first speaker, Kip Allander.
Okay, great. Thank you, Levi, for that introduction. So my name is Kip Allander. I'm a hydrologist with the USGS Nevada Water Science Center, and I'm going to be giving the preliminary results of the Humboldt River Capture Study. This is a very big, large modeling effort between the USGS and the Desert Research Institute to estimate capture depletion in the Humboldt River Basin. I'm going to be presenting results from everybody's work today. So I do want to take some time to recognize all the contributors to this presentation. So the Humboldt modeling group consists of four major teams. Humboldt ET, which is led by Justin Huntington and Matt Bromley of the Desert Research Institute. The Upper Humboldt model, which is led by Rosemary Carroll and had a lot of assistance from Greg Pohl while I was still with the DRI. And then the Middle Humboldt model, which consists of Kyle Davis, William Eldridge, Justin Mayers, and myself from the USGS. And then the Lower Humboldt modeling team, which is Karen Nadler of the USGS and Susie Rybarski of the Desert Research Institute. So this map on the right shows the domain of the three principal models. The Upper Humboldt model is the entire Humboldt River Basin above the Carlin Gauge. The Middle Humboldt River Basin model is the domain between the Imlay Gauge, just above Rye Patch Reservoir, and the Carlin Gauge, and extends up to the Upper Reese River Valley, but does not include the Upper Reese River Valley. And then the Lower Humboldt River Basin is the basin drainage area below the Imlay Gauge and includes Rye Patch Reservoir and the community of Lovelock, as well as the Humboldt Sink. So this graphic shows a conceptual model for the Humboldt River Basin, and it's really representative, mostly representative of the Middle Humboldt model, and demonstrates the various processes being simulated within the model, which includes the groundwater system, the inflows and outflows of the groundwater system, including recharge from the mountains, from the rivers, from irrigation, as well as discharge by groundwater evapotranspiration, diversions, pumping from agriculture, from municipal supply, as well as for industrial and mining uses. And then it also simulates the Humboldt River and tributaries in a dynamic fashion using the streamflow routing package, which allows us to simulate the changes in dynamics of streamflow through time. And it also simulates the diversions from the Humboldt River used for agricultural irrigation. The upper model and the lower model are a little bit more simplified than the middle model because of different purposes and different processes that are occurring in those regions. And those will be explained more fully at the stakeholder meeting coming up in the first week of February, which I'll announce at the end of this presentation. So I'm going to start by sharing some of the results from Justin Huntington's work on the evapotranspiration discharge. This was for the entire Humboldt River Basin. And really, this is just a single slide to summarize all that work that he did. The map on the left shows the areas of mapped potential groundwater discharge. This was a significant effort using Landsat imagery, high-resolution digital elevation models, some field verifications to update the boundaries where groundwater is potentially discharging as evapotranspiration. And then he used that along with satellite imagery information, time series of satellite imagery, as well as the relationship between vegetation indices, as well as gridded weather data to estimate groundwater ET over time since the mid-1980s when Landsat data became available, and developed a overall discharge distribution for the basin, and that's shown in the middle map. And then the map on the right shows the Humboldt River Basin by hydrographic area with the total estimated discharge through evapotranspiration, groundwater discharge through evapotranspiration. And so you can see that not all basins are equal. Some have much greater discharge than others. And so this is just kind of like a final summary of that work. And Justin's going to present this work in more detail at upcoming stakeholder workshop. I got more information about that at the end of this presentation. So next I'm going to talk a little bit about the stream efficiency in the middle Humboldt River Basin. Recall that the middle model simulates monthly stream flow, and so it allows us to really take a closer look at some of the stream dynamics and some of the properties of the stream flow. And this is going to be a series of slides I'm going to walk you through to help understand the results and what we're displaying. So this chart is showing what the actual observed stream efficiency is in the Humboldt River between the Palisade gauge and the Imlay gauge. And it's probably important to mention here that stream efficiency, as defined in this application here, is the proportion of the flow at the Imlay gauge that passed by the Palisade gauge. So if the efficiency was above 100%, that would indicate there's greater flow at the Imlay gauge and that there's somehow a system gain occurring during that time period. Whereas below 100%, that indicates that water is being consumed or lost in the system between the Palisade gauge and the Imlay gauge. And it's well known that in the Humboldt River Basin, in general, it's a losing system, and for the vast majority of time, the conditions are losing between Palisade gauge and Imlay gauge. But there are times when there's flow inputs in between those two to drive the efficiency above 100%. So this chart shows the observed monthly stream efficiency, and it's quite noisy, and it makes it hard to really look at and to use when it is this noisy. So one of the things we like to do is to just smooth that signal out, and we use a 1-year running average to look at the data, and that's what this is showing, the actual observed 1-year running average for the stream efficiency between Palisade and Imlay gauges. And you can see is that for the most part the stream efficiency is below 100%, and in particular during the drought after 2012 through 2015, there was really a substantial decrease in the observed efficiency. Well, and to state it another way, the Imlay gauge actually dried up during that period, but the 1-year moving average indicated efficiencies that were under 10%. I think another important thing to point out in this curve is that the y-axis is stretched out over 3 log cycles, and so it tends to squash the high values and expand the lower values, and so it is kind of a different way of looking at it, and that's an important consideration when looking at this data. So what we want to do is compare the observed one-year running average, again here in blue, with the simulated one-year running average from the Middle Humboldt model. And you can see that for the most part, the model is doing a pretty reasonable job at estimating that one-year running average of stream efficiency. There's a few departures in more recent time, and then most recently during the drought, it doesn't quite track as well, but I want to remind that this is a log scale, and so the differences get exaggerated in these lower values, and so it's really not as bad as it looks because it is on a log scale. Now we want to take a look at this in a different way. So the red line is the simulated stream efficiency for the Humboldt River, and that is from the calibrated model, which has pumping occurring in the model. And so what we want to do is say, well, okay, what would happen to the stream efficiency in the system if there was no pumping occurring? And so that's what that yellow line is, and it shows that this departure begins sometime in the 80s, where the model indicates that there's a loss in stream efficiency from pumping, and then all the way through the 80s until the mid 90s, and then all of a sudden you see this reversal where the simulated model without pumping actually has lower efficiency than what was observed in the river. We'll talk about that in 1 second. And then we have this reversal again around 2005, where the river is now less efficient than it would be without the pumping. So the next slide I'm going to show is really taking the difference between these two curves, and so we call that the change in stream efficiency. And this is really the part I wanted to get to. And of course, during the beginning of simulation time, there's really no difference between pumping and no pumping, and so there's not that. So it's around a 0% change in efficiency. But over time, with pumping and depletion of the river, you start to have this loss in the stream efficiency that occurs. But then in the mid 1990s, you can see that there is a big increase in the stream efficiency, and it goes above zero, and the change in efficiency, and it goes above zero, and then again drops down in 2005. And so what is going on here? Well, that was the period when the Lone Tree Mine was being dewatered, and all that water was being discharged to the Humboldt River. And so that's a real important finding, and to be aware of this, because the river really wasn't that efficient. It just appeared that way because of this new source of water, where it was being removed from the ground and being directly placed in the river. And so that kind of obscures this analysis. But what's really neat is because we're using a model, we can remove the entire impact of the Lone Tree Mine on the Humboldt River efficiency, or the change in the efficiency. And that's what we look at here, is we just say, okay, what if Lone Tree didn't have any influence on the river? And so what we see here is that over time, the stream efficiency of the Humboldt River has been decreasing, and has decreased by upwards of 20%. It fluctuates through climate cycles. So during wetter periods, there tends to be less of a loss in the stream efficiency, and then during drought periods, it's an increase in that loss in stream efficiency. And so this will be really important to help the state understand the potential impacts to the distribution tables, and how they use those distribution tables in the Middle Humboldt River Basin, and how to manage for conflict. And I want to make sure everybody's on the same page as far as what is stream capture. And so by strict definition, stream capture is the reduction in stream flow that's caused by a pumping well. And so to help illustrate this, the panel on the right shows the physical process that occurs and what the source of water is to a well when it's being pumped. The top panel shows a system, a hypothetical system that's in a dynamic equilibrium. Of course, there's no pumping going on, no changes in storage. All the recharge is going to discharge. Some of that discharge goes to ET through phreatophytic or riparian vegetation, and other discharge goes to streams or springs. Now, the second panel there shows a well being introduced and starts pumping. And when a well first starts to pump, water initially comes from storage, from groundwater storage from adjacent and around the well, and it starts to draw down the water table. And as time proceeds, as we move to the third panel, that drawdown continues to go down, but it starts, the cone of depression starts to reach out and starts to impart gradients towards other boundary conditions such as streams or towards that phreatophytic vegetation. It starts to lower the water table below the phreatophytes, and when the water table is lowered below phreatophytes, they're not able to use as much water, so that becomes a form of capture because you're taking that water away from the phreatophytes. But it also can reduce the outflow to stream or increase the recharge from the stream to the aquifer in order to supply the water to the well. And then eventually it reaches some dynamic steady state in which the storage is no longer changing and it's getting a fraction of its flow to the well from the streams and from the capture of ET. So this is also expressed in the chart on the left, and this is what we call a capture curve or capture curves, and it shows the same behavior, but it shows it more graphically. Basically at time 0, when you first start pumping a well, all the water comes from storage, or 100% of the pumping is coming from storage. And then as time goes on, less water is coming from storage and more is coming from stream flow capture, and then also from ET capture. Now, an important distinction I need to make for the rest of this presentation is that the USGS refers to stream capture as stream flow depletion. They're the same exact thing, but the USGS prefers the nomenclature of stream flow depletion. So now we want to look at the stream depletion with pumping for each of the basins, and we'll start with the upper Humboldt River Basin and work our way downstream. So this chart shows the annual pumping through time from 1960 through 2015. Notice the scale on the left, pumping ranges around, more recently, around 23 to 30,000 acre feet per year. It was really low in the early 1960s, less than 5,000 acre feet per year, and ramped up in the 1970s and the 1980s, and has been mostly steady or decreasing slightly since then. And then the blue curve shows the estimated stream depletion as a result of the pumping. And of course there was no stream depletion at first, and then over time the pumping starts to have increasing influence, and what we see is that the stream depletion starts to get upwards of around 10,000 acre feet per year since around 2008 or so. And the other interesting thing about this is that represents about 45% of the pumping rate in recent years. And so I'm going to show the results for the middle and lower basin. You're going to see that the relative amount of capture from the pumping in the upper basin it tends to be a bit higher than in the middle and the lower basins, and we'll kind of talk about that in the future slides. So this is the same chart for the middle Humboldt River Basin. Notice the scale on the left is an order of magnitude higher than it was for the upper basin. So in the 1960s, very little pumping was going on. It ramped up during the 60s and 70s, and then leveled off some in the 1980s. Until the early 1990s, and then there's a steep increase in pumping in the mid-90s into the 2000s. Of course, that increase is due to the mining operations and dewatering for extraction of the ores. And since the 2000s, it's kind of leveled off and decreased to some extent over the years. But our annual pumpage is on the order of 350 to 400,000 acre feet per year in the middle basin. But now if we look at the stream depletion and the relative percent of the pumping, it's quite a bit less than what we saw in the upper basin. But if you actually look at the magnitude of the stream depletion, it's about the same, on the order of about 10,000 acre feet per year, to as much as 20,000 acre feet per year since 2006. But the actual percentage of the overall pumping is quite a bit less, at only around 3 to 5% of the pumping. So now we can take a look in the middle basin at that stream flow depletion, that blue curve that we were just looking at, and dig a little deeper into the analysis. So showing the same curve, but this time we've done it as a stacked area curve to show the relative influence of pumping from each of the hydrographic areas in the middle basin. And so this allows us to kind of get a sense of what that impact is on the stream depletion by these hydrographic areas. And what we see is the Winnemucca segment has the greatest impact on the stream flow depletion, which isn't surprising because it's right along, that entire segment is right along the river, followed by Paradise Valley, which has a substantial amount of pumping. It's a little bit further away from the river, but it's a substantial amount, followed by Grass Valley, Clovers Valley, and then lower Reese River Valley impacts. The legend on the left lists all of the valleys that consist of the Middle Humboldt River Basin in decreasing order of impact on stream flow depletion. And this plot just does not include the impact from mine dewatering. Now moving downstream to the Lower Humboldt River Basin. Should be getting familiar with this chart by now. Again, showing pumping and estimated stream depletion. Notice the scale on this graph here, though. It's only 0 to 5,000 acre feet per year. There's very little pumping occurring in the Lower Humboldt River Basin, mostly for municipal use, a little bit of mine operation, industrial operations, as well as some supplemental groundwater agricultural use. And so the pumping in the lower basin is much more influenced by supplemental groundwater, and that's why you see this great variability in the pumping. But it's increased gradually over time. It seems like there's been an increase in the amount of supplemental groundwater use over the last 20 or 30 years. Here the stream depletion is only around 300 acre feet per year in more recent time. So it's really not a substantial impact on the flows on the lower basin. But it does represent between 7 and 14% of the actual pumping. So now we're going to look at some capture maps starting from the upper Humboldt, moving our way down stream. And this is after these maps were drawn for a period of 10 years of pumping. This is basically the impact of pumping from any given location on the stream flow depletion after 10 years of pumping. And the first thing you notice with the upper Humboldt River Basin capture map is the density of the drainage network really shows up, and that's one of the reasons why we saw such a much higher relative capture in the upper basin, because pumping is generally a lot closer to the tributaries and the sources of water to the Humboldt River Basin, and so it's easier to impact the system when you're closer to the rivers. That happens in a shorter duration period of time, and that's why we see this relative impact, and that's why we have a much greater estimate of the impact of pumping in the upper basin than the middle and the lower. So Rosemary's going to show this map as well as 1-year and 50-year maps at the stakeholder meeting coming up in February. So you'll want to tune in to see those results as well. So for the Middle Humboldt River Basin, this is the 10-year capture map, and we do capture maps in the Middle Humboldt River Basin 2 different ways. One way is relative to the stream flow at inlet gauge. So pumping anywhere in the basin, how it affects the stream flow at the inlet gauge, and that's what this map is showing. And you can see that when you're near the river, you have greater impact on the stream flow than when you're further away. That's just the nature of stream capture. And so that's what we see here. We also do what we call a system depletion map, which considers a lot of the tributaries and as well as the other perennial reaches of river or streams in the Middle Humboldt River Basin that may or may not be connected to the river. And those are going to be presented in a different map. And hopefully we'll have that available for the stakeholder meeting, but if not, it will be in the report and the final analysis. And then moving downstream to the lower Humboldt River Basin, this is the capture map after 10 years of pumping. And of course we see the same pattern where capture occurs along the river within 10 years. That's an expected result. Some places it's closer, some places it's further away, and that's because of the heterogeneity of the aquifer properties in the system. Kara and Susie will be showing more maps and other results at the stakeholder meeting, so please come to that. So now, the capture maps are nice tools, and they're very useful for being able to visualize and picture the relative connection between groundwater and surface water. So you can see how the patterns are, how things are kind of connected, and how pumping is going to impact the river. But for management purposes, they're really not that useful because it's hard to get into a very specific location and to extract for a very specific time of pumping. So what we've done is developed a tool that we call the Humboldt Capture Query Tool that allows the users to query the results of the model so that they can get very specific results for location, depth of pumping, as well as duration of pumping. And the image on the left shows the query side of the tool where you can basically zoom in, you put different types of maps or overlays on this, zoom in, select a location, you can actually select the location of your well, or you can enter the location as a latitude, longitude, select the depth of your pumping, and then the duration of your pumping, and then it extracts the results, which is in the image to the right. And it extracts the full capture curve. So you get the depletion through time, you get the salvage DT through time, as well as the changes in storage through time. It shows you the up to 100 years, but it also gives you a return on the exact years that you've entered for your site. So it's going to be a really useful tool for actually knowing what the capture is at any given time for any given location throughout the entire Humboldt River Basin region. So that concludes this presentation, but I do want to thank you for bringing it up and watching it. And before I end, I'd like to make a couple of announcements. First off, I want to put in a plug for a presentation that's going to be coming up on Tuesday at 9 a.m. on the behavior and prediction of stream capture under varying stream flow conditions, being given by Stephen Jepson from our office. So this is related to the Humboldt work for us. This is our effort to better understand how stream capture varies or can be impacted by varying stream flow conditions. Steve has been putting a lot of work into this, and I had a sneak peek at that presentation, and it looks really good. So I really recommend going and having a look at that presentation. Next, I definitely want to promote and to announce the Humboldt stakeholder meeting that's coming up next week on February 4th at 8:30 in the morning. Anyone can attend because it's a remote meeting. And the address to attend is listed on the slide. It's on the Life-Size Cloud application that the state offices use for large meetings. So please come to that. You'll get to see a lot more details and a lot more results from all of the other modelers and others that have put effort into this work. And then also I want to make sure everybody knows to come to the question and answer session at the end of our session here. That'll be on January 25th at 10 a.m. in case you're watching this presentation early. And then last, I want to announce the talk that follows this one in this panel, and that's by Dr. Michael Taylor, and he's going to be talking about the money, the Humboldt River Basin, and specifically the money of water, the cost of water. And his talk is titled Economic Analysis to Support Conjunctive Management of the Waters of the Humboldt River Basin. So again, thanks for your time. And I look forward to seeing you at the question and answer session. Thank you.